3.2i and j are going to show you how to use the standard deviation of the residuals to assess how well a model fits the data and interpret it in context, and then use r squared to assess how well the line fits the data and interpret it in context. First, let's define the standard deviation of the residuals. If we use a least squares regression line to predict the values of a response variable y from an explanatory variable x, this value gives us the approximate size of a typical or average prediction error. So basically what the standard deviation of the residuals is on average how much error we could expect from using our model. It's defined by the lowercase letter x, and the calculation for it is you're going to take the square root of the sum of all of the residuals and you divide it by n minus 2. You will not have to know this detailed formula for it, but you will need to know how to define it in context. Let's do an example. Going back to our 11 Honda CRVs, for the model that we found, the standard deviation of the residuals is this value right here, 792. They basically just want us to interpret this in the meaning of the context. A very good way to say this is that when the miles are used to estimate price, we will be off by an average of $972. So if we use the model that we came up with to predict the price using the number of miles on the CRV, on average we're going to be off by $972. That is what the standard deviation of the residuals means in context. The second thing I want to tell you how to define is called the coefficient of determination. And what it is it's r squared. It technically is just the correlation value squared. And what they've done for it is this. You can see right here they're doing a proportion or a percent. So by definition what it is a percent of variation in the values of y that is accounted for, scroll over here, by the least squares regression line. So this specific proportion right here, the SSE is the sum of the squared of the errors. And what that is a summation of all the squared residuals. That is the total variation in predicting y. And then this value here, the SST, is the sum of the square of the total. And what that is, SST, is the summation of all of my y hats minus the y means squared. This, by definition, is the total variation in just the y's. So what you have is the SSE, or the sum of the squared, the error, is all of the squared error or residuals. The SST is the sum of all of the y values. So this is going to give us the portion of the error in the model. If we take 1 minus the portion of the error, it's going to leave a percentage that's left over, and it's going to tell us what's left over is how good the model is. So overall, what r squared is, it's called the coefficient of the determination, and it tells us how well the least squares regression line predicts the values of the response variable. And again, I already kind of talked about this. How is r squared and r connected? Very much directly, in that r is equal to the square root of r squared. So if someone told you r squared, you could actually compute the correlation from that. If someone told you correlation, you could actually square that and get the r squared, which is called the coefficient of determination. So now how are r squared, which is coefficient of determination, and the s, which is the standard deviation of the error, related? Well, both of these measure fit, and they tell us how well the line fits the data. But the one difference is this: r squared is actually going to be a percent of how well it fits, whereas s tells us about the average amount of error in our prediction. It's good to know, again, r squared and s by definition and context, because typically you're asked to define one of those on a true free response in the real exam. So here's a good real life application. The used Hondas. If we take the r value or the correlation and we square it, we're going to get 76.4. What does 76.4% mean in context? A great way to say it is just this. that 76.4% of the variation in asking price can be accounted for by the least squares regression model, which was used to relate asking price to the number of miles driven. Now, the remaining variation, so the remaining percent here, which we're talking about, 23.6%, is due to other factors, such as the condition of the car, the age of the car, other lurking variables. All that we know here is that the miles driven, as it relates to price, explains price 76.4% in total. And that means there has to be other variables out there that help explain the price of this vehicle. Here's a really nice multiple choice question. For the least squares regression of fat gain on NEA, so on the national average calculation of something, they came up with an R squared of 0.606. Which of the following gives the correct interpretation of this value in context? Well, if I read letter A, 60.6% of the points lie on the least squares regression line. That's clearly not a true fact of what it means, so I'm going to cross it out. I'm going to jump to letter D, where it talks about 77.8% of the variation. The 77.8, I suspect, is the actual R value, so that's not correct. We want the true R squared, so I can go ahead and cross D out. So it comes down to, is it B or C? Is it 60.6% of the variation in fat is accounted for by the least square regression line? Or is it B, that 60% of the fat gain values are accounted for by the least square regression line? Is it the variation in the fat gain, or is it actually how the fat gain values are computed? It is very specific. Whenever you see R squared or coefficient of determination, it is always about the variation in the Y value. So it is clearly in this case not going to be B, and the correct answer here is C. Here's another good multiple choice. A recent study discovered that the correlation between age at which an infant first speaks and the child's score on an IQ test given upon entering school is about a negative 0.68, so that's the correlation. A scatter plot of these data show a linear form. Which of the following statements about this finding is correct? Is it that infants who speak at a very early age will have high IQs by the beginning of grade school than those who speak later? This never says anything about those that speak later, so that's clearly not going to be part of it. 68% of the variation in the IQ scores is explained by the least squares regression line of the age of the first spoken and the IQ score. So this is the definition of R squared. This is R, so this is not correct. If we take this and square it, it is not 68, so I'm going to cross off this one. Encouraging infants to speak before they are ready can have a detrimental effect later in life. I'm not even going to continue to read this. That's just a conclusion someone's making. I have no clue where that's coming from. It does have to be D in this case. There is a moderately strong negative linear relationship between age of the first spoken word and later IQ. That is what the definition of R is telling me is the DOFs of the relationship. So don't forget your direction, form, and strength when you're given a correlation or R. This slide here is just good to talk about in terms of how to analyze data, and we've said it time and again. The first thing you really want to do is to plot your data and see a scatter plot so you know if a relationship is linear. If it looks linear, talk about the DOFs of it in terms of direction, form, strength, and the outliers. After you've done that, you're going to move on and maybe you're going to look at the numerical summaries. Maybe you compute the linear regression model, or you look at the means and the standard deviations or the R value. These are all values that are used to compute the regression model. Then after you do that, your last step is going to be to actually make your residual plot. Look at the residual plot to see if you can feel like it really is a nice linear relationship where we're looking for no pattern in our residuals. So going through these 3 steps is really a nice logical order. Some things to be cautious of. Good linear models can have a low R squared because the underlying relationship is linear, but it is weak. So if you see an R squared, again, the coefficient of determination, how much of the variation in the Y value is explained by this model. If it's low, it could still be a good linear model, so you just have to be cautious of that. A low R squared doesn't mean it's bad. Look at the scatter plot, look at your residual plot. Number 2, a bad linear model can have a high R-squared. And when you look at the data, though, it might be curved and not linear, which means always look at the picture of the scatter plot. This is a good first starting step. And number 3, just because R is high or R-squared is high doesn't mean we should use a linear regression. Always check the residual plot. The overall moral of this, we've said time and again, is always look at both the scatter plot and your residual plot to determine if you think a model is linear.